All right, everyone. Good morning. Um, so just I guess delineate the path ahead today. We're gonna finish the wrangling exercise. Um, and after that, we're gonna have some quick slides on Git and GitHub. If you have not used those before, I hope these are helpful for you to understand, get some idea of that. I also hope that you had a chance to go through some of the reading material related to that Happy with Git R ebook that I had listed on the course website. And after we go through those slides, depending how much time we have, we're gonna then set up Git and GitHub on your own local machines. If you already have that done from previous, experiences or maybe previous classes, then you're probably a little bit ahead of the curve. If you have never done that, don't worry, we're gonna go through step by step to make sure that everyone has a working version of Git connected to GitHub properly. Because then we're gonna be making use of that. Me, when I'm sharing the files, I'll continue sharing files on that 2024 DSA. But after today or potentially next class, you will be equipped to, instead of downloading manually, to simply do a Git pull from that repository, which is gonna help you a lot. That's just from my side, but also on your side, once we get Git and GitHub working on your computers, I do want you to every single time that we create a new project here inside of this course folder, for that to be a Git repo or a Git local project in your machine, but also connected to your own GitHub account through a repo that you're going to be doing all the Git actions that we're going to learn through that. So just really want you, because I know some classes you may learn about Git and GitHub, you may not use it a lot. Here we're going to be using a lot once we're all set up to do that. Okay, so first thing is that we're going to finish the wrangling exercise. I'm looking right now at the main folder for this course. You should see something somewhat similar where we have, the 2024 DSA is that GitHub repo that I use. On your side, this is probably called 2024 DSA main, as you've been downloading from my GitHub repo. We also have the 01 intro. That's where the files for the intro lecture were, and the 02 wrangling as well. That's what we're gonna keep working today. So if you go ahead, open that. A reminder here, I will be so repetitive with this that I hope you get sick of me saying this. If you're working in our studio, you're using our studio projects, always make sure to launch this project by clicking on the R proj icon. Do not launch a script by double clicking on the script, because that, as we talked already about, will set you in the wrong relative paths if you're not working through the same or working through the proper RStudio project. So go ahead and double click on that 02 wrangling R proj if you don't have yet that project launched on your computer. Again, how do you know you are in the right project? So make sure that the name that appears on the top right is matching that project that you were intending to open. If this says project none, then you're not in the right project. Go ahead, go back a step and open through what we just showed. And if you're not, so in my case here, when we stopped last class, we stopped right here at soy K4. So I'm going to review a little bit of what we did previously, but just to let you know, because last time I saved the script and simply closed my RStudio window, now that I reopened this project, it already shows me that script open for me exactly where I stopped. So another benefit of using RStudio projects, it really sets you up for that project in a very nice way. In case you don't have the script appearing there, but you are in the right project, you would come here on the right-hand side, go under the Files tab. I always like to click the R blue button to take me to the main folder of this project so I can more easily navigate. So if you do that, you should be seeing something like this, where if your script is not popped up, you would come under Code and then just click on that script to make it appear on your working environment. All right, this is just a review of what we've been through. So now let's just see what have we done already on the previous class. And if you would, please come and run these lines of code, because I hope that your environment is empty right now. That means that you did not save your previous R environment, which is something that we talked already about. We don't want to do that. So that means that you have to rerun the code that you already developed up until the point that we developed. So if you recall, this is an R markdown file. So we have narrative, code, and output all integrated. To run a whole chunk, which is what we want to do here, we can just go to that play button. So I'm first going to load all the packages we're using today. Next chunk, we're reading in this data. So we're using the read Excel function to read an Excel file into R and have that as an object. Here we use the view function to see that entire object. So it has 16 rows. So 16 observations. It has, I think, 8 columns. If we print, 8 columns. So if we print here, we see that better. Just to refresh your memory, this data set here is a study that, especially if you are in row crop agriculture like I am, and I know some of you are, this should look very familiar to you as one of the data sets that you could potentially collect from your own studies, where we have plot number here, we have treatment number. The stage is just the crop stage that was collected. So in soybeans, it was the R4 growth stage. Our treatments and potassium rate ranging from 0, 50, 100, and 150 pounds of K2O per acre. So just different rates of fertilizer. And we're interested in measuring at this crop stage of R4, what was the soybean trifoliate potassium concentration. So how much concentration there is in the soybean leaves. And we did this study in 4 locations, and we have a column for each location here. So Tifton, Midville, Watkinsville, and Macon. And this study, again, just to refresh your mind, was a randomized complete block design. We have not talked about this in specifics yet. So if you don't know what that means, it basically means that we have full blocks where each treatment appears once in each one of those blocks, and we have 4 blocks in this study. I'm not going to focus too much on that aspect right now, but if you know what that means, at least we have some more context here. So we used afterwards, we used the function glimpse just to get a glimpse of this data. So that shows us how many rows, how many columns, what are those columns. Already gives us how R is interpreting these. This is right now, we're not gonna worry much about it, but I do want you always to be thinking about whenever you read data into R, always make sure to understand how R is interpreting those columns and what class R is interpreting them as, because this will become important when we start running analysis. So right now plot is, so DBL stands for double, that's numeric. So R is seeing everything as numeric except for stage because it has a letter there. So if you have a letter just even in one cell of a given column, R will see that and treat that as character. Then we ran the summary function after that. So here was just inspecting, right? Just understanding how things are interpreted, getting some summaries on the numbers. You can go ahead and run that summary as well. Just a quick refresh. If your columns here are numerical, the summary function gives you a statistical summary, which can be useful to find, mistyped data or maybe data that is weird as far as having a minimum or a maximum value that is not biologically possible, it doesn't make sense. So let's say if you had a potassium concentration that was a negative number, that is definitely not possible, right? So it would be an entry error. You have to go back to the data and fix it. Or if you have a concentration that is, over 100, definitely would be wrong. But even like in this case, leaves don't normally have very high concentrations of potassium. So if you have even a concentration above 10%, that would be already biologically suspicious that you would inspect that. All right, so then we imported this data frame called soyk, or this Excel file. We assigned that to an object called soyk here in R, and then we started doing some wrangling. So the first thing that I proposed here was that we use the function clean names just to standardize the column names first. So I'm going to just print soyk so you can see again. So soyk, all the column headings are non-standard, right? So we have plot with the P uppercase, treatment all uppercase, stage all lowercase. We have white spaces. We have special characters like parentheses. These are things that we want to avoid when we're dealing with any type of data. In this case here, we only had 8 columns. So maybe you could change this manually. I'm not going to show you how to do that manually, but let's say you have a very large data set. Maybe you have 50 or 80 or 100 or 200 columns. Now it really becomes impossible to do by hand. So clean names, if you run that, it gives you this function comes from the janitor package. It has more useful functions that you can explore on your own if you wish, but clean names is one that I use commonly, which basically just standardizes all of your column names. So now everything is lowercase. If there was a white space, it was replaced with an underscore. If it had a parentheses, that was removed. Now these columns are short, concise, easy to call them whenever we need to make a plot, make an analysis, whatever it is. Next one, I just showed you the filter function where we wanted to keep only the rows that had a potassium rate equals to 0. So this double equal sign here, we're using double equal sign because it is a Boolean operation. So we're trying to create a condition based on a column and the given value. So we're saying I want something equals to something else or different or greater than or lower than. That's what this is double equal sign. And I'm just showing the filter function here. We're going through it and assigning that to an object called soyk2, which is using soyk1 as the incoming data frame. Soyk1 was the one that had clean names applied to it. So go ahead and run that as well. You should be running these and making sure you have them on your environment, because whenever we get to the next few steps, we're actually going to be using some of these objects. Next, one of the columns that we had was potassium rate in pounds per acre. I wanted that to be in kilograms per hectare because maybe you're writing a paper or maybe you have a conference that requires international units. So we took soyk1. Notice how we skipped soyk2. So we're not using soyk2 in the next step because this was just to show the filter function, but I wanted to move forward having all the data. So we bring in soyk1 again. We use the function mutate to create this potassium rate kilograms per hectare, which is just a function of potassium rate pounds per acre, which we already have in the data set. And then we use again, we're basically overriding the rate kilograms per hectare again on the next row or the next row of code here, where we're just rounding it to 0 digits because I really don't care if it is, 54 point something. I just want to know 54 or 56, I think is the value that would be. So make sure you run that. So we already went through this previous class. I'm just making a quick overview here. So now at this point, soyk3 has all the column headings standardized through clean names. And it has this potassium rate in kilograms per hectare column that we transformed from the pounds per acre. Okay, so come to the next chunk here called soyk4. And so if you are in my other class, this is probably the last exercise that overlaps with that class. So if you are in that class, you already know what I'm going to ask here. So you can just skip answering because I already know the answer. I want someone else that has not done this before to help me here. So for us to run a analysis of variance model, in this case with a randomized complete block design, we need to have a column that says block or rep number, which if you inspect closely, we don't have that yet, right? However, we do have one column here that can help us to learn that information. So I'm just printing here a soyk, or we're seeing right now soyk3. We're seeing some of the columns of it, but even just within this view here, you can already think about this issue. So if this is a data set that's given to you, or maybe this is how you bring your data from your own study that you type back in your computer, how can we learn block number or replication number based on what we have right in front of us?
Just looking at the treatment.
Okay, so which column would you look at?
Column 2, the treatment one.
So the treatment column?
Yes.
Okay, so how would this help you to know what is the block?
So there are 4 digits, 4 values of 1, 1, 1, 1.
Mm-hmm.
I can call it block 1, block 2, block 3, and then block 4.
Okay, that is one way to do it. Now, what if the person that was collecting this data actually did not follow that order? So maybe this is block 1, but this may be block 4. This may be block 2, and this 3. just by looking at treatment number and assigning it that way, it works if the order is correct, right? But what if it's not? Is there another column here that can help us to do that? To learn what's the block number? Plot, okay. How so?
155 would be the first block. 203 second.
Okay. Okay, so what Anis is saying here, and I just want to maybe say in a slightly different way, is if you ever conducted your own studies or helped someone else on the field, normally, or I mean, it doesn't have to be in the field, I guess, but I'm thinking of field because that's what we do the most. You would have your plot numbers will start with the number of the block, right? So normally your hundreds, so 101, 102, 103 would all be plots inside of block one. Your 200s will be plots inside of block two, 300s plots inside block three, and so on. So if you come here and this is what you get, you don't have a block column, but we have a way of learning that from the plot number, right? From the plot column here. So that's what we're going to do next here. So if you come on soy K4, we want to create a new column that I want to call rep, which is in this case is equivalent to block. So every time that you're thinking of a new column, I want you to be thinking about the mutate function. So let's do a mutate here. The first argument is always the incoming data frame, which is going to be soy K underscore 3, the one that we created just above. Right, so soy K underscore 3. I want to give it a comma and hit return just so we break the code and make it easier to read. And now we give it the column name that we're creating. So I want to create a column named rep. And then we give one equal sign, and then we say how we're creating it. So because we're going to be creating conditions, right? So if you think about it, we're going to say, we're going to set conditions based on the plot column to create the values of the rep column. One way of creating conditions, if you've been doing this even in Excel or a different programming language, it would be to use an if-else function. So it would say, if else this condition is true, then this happens, and if this condition is false, then that happens. There is an if-else function in R, there are if-else controls in R. However, if you have multiple conditions, what ends up happening is you have to start nesting if-else statements inside of one another, and it works, but it doesn't look pretty. And I mean, I don't mean pretty by pretty, but it doesn't look intuitive, I guess is what I should have said. So when you read an if-else nested statement, it looks messy and it's hard to understand what's going on. So instead of using if-else statements, we're going to use a function from the dplyr package called case when. You can start typing that. Open and close parentheses. I'm gonna hit return just to make it easier for me to read this code. So let me ask someone else. Don't think about code terms, like coding terms, but just think of like words. If you were to explain to someone what you would do here, what would be the condition you would give the software to create the first block? And again, you don't even have to look at the code itself, just look at the data frame and think with me, what would be the condition you would give to create the rep being number one? Just in words. Okay, the initial number.
Or between 100 and 200.
Yes. We could go both ways, but let's take that second route there. I think it's going to be easier. So if we just say, for example, if plot, and you can start typing with me as well. So if plot is greater than 100, then rep equals to 1. So if we just say this right here, it's going to look at the plot column. If that number is greater than 100, it's going to say that the rep value equals to 1. This is the notation we would use. If you just go ahead and run that, and then you print your soy K4 results, what happens is that everything now is rep 1. And that's because we didn't put an upper limit on this condition, right? We just said if plot is greater than 100, which all of them are, then rep equals to 1. So let's come back to this code and fix that. Let's give it an upper condition as well. So for that, we come here, so we say plot greater than 100, you add an and symbol like that, and then we say plot less than 200. Oops. So anytime plot number is between 100 and 200, that cell is going to receive a rep value of 1. If we go ahead and we run that, that should work. And if you print it, and you just go to the right here, just look at your rep column, it did exactly that. So if you were to come back here, you would see that the first row in this data frame is 105, I think. And then 2, 3, 4, the fifth row is 100 and something else. So 102. So it is doing that. But now it filled everything else that did not match this condition with an ace. And that's because we did not specify the other conditions, right? So let's just keep building here. So the way that we would do that is add a comma, break code to make it more readable, and then give it the next condition. So based on what we just did here for rep 1, how would you specify the condition of rep 2? And now you can speak in terms of the code. What would you say? What would be the condition for rep 2? Plot greater than 200 and plot less than 300. Tilde 2, right? Yes, so if we do this, it's going to basically apply that concept. Now everything that's between 200 and 300 receives a 2 under rep. That's exactly right. Thanks, Anis. Now let's just keep going here. If I come and just do for the next condition would be if plot is greater than 300 and plot is less than 400, then rep equals to 3. And then lastly, because we have 4 blocks only, we can just give a lower boundary here. So we can just say anything that's greater than 400. So if plot is greater than 400, then rep equals to 4. Right, so if you run this and then you print your result, you should be able now to see your rep numbers all down the data frame, no NAs, everything is matching correctly. Nice. So this is one example. It's a very simple example of how to use case when, and I wanted to expose you to this simple example so you understand the syntax and when we use it. I use case when a lot in my data wrangling tasks, and even in very complicated situations where you have multiple conditions and different things. Anyways, I just wanted to expose you to this function because I think it can be very useful. Anytime you think of if else, I use if else's if I really just have 2 conditions. So if I had block 1 and 2, it's probably easier to use if else. However, if I start having more than 2 conditions, then you need to use nested if else statements, which then starts to become very difficult to understand your code. And here we're looking for code that is intuitive, that makes sense, that you look at it and you know exactly what's going on. So I would recommend you use case when in those cases. Okay, so let's go to the next step here. So the next step is, let me just, let's just look at soy K for a second here. If I want to run a model or even make a plot where I consider the location. So let's say I want to color lines by location, or maybe I want to have a random effect in a model that is related to location. I need to have a column in this data frame that has the location information under it. Right now, we do not have that. And I just want to give you a quick moment here to look at this data and think with me. Where is the location information right now? In the columns, right? So it is in the column names. That, if you read the tidy data concept, that is not tidy data, right? Because you have information that is you need in the columns where they should actually be in rows under a column, right? So the next step here is basically us bringing this information from rows to columns. I'm sorry, the opposite, from columns to rows. So we have a column that has the location information that then we can use after that. I think we already talked about the names function. It basically just prints the names of the columns. Sometimes I do that just to remind me in like a quick copy and paste from here if I'm doing a wrangling exercise like this. So that's why I left it there for you. Now, the next step here, we will pivot longer, and the function is called pivot longer. So it's very intuitive, where what I want to do here in the next step is we have 4 locations, right? So Tifton, Midville, Watkinsville, and Macon. And right now our data frame has 16 rows. What I want to do here is basically create a new column that, I mean, can be called anything, it's customizable, but let's say we call that column values. And then I take all these 4 columns that right now each one has 16 rows, and I stack them below each other. So I take the first 16 rows for Tifton, and then I take the next from Midville and put right below it, and the next from Macon and right below it, and so on. So my data is gonna change from wide to long, right? We're gonna decrease the number of columns, increase the number of rows to do this. And also, when we do that, we also need another new column that's gonna have now the column headings that are currently column headings, but it's gonna go under that column. So imagine that all the values now that are coming from Tifton, there's gonna be a new column called, let's say, location, that's gonna have Tifton, Tifton, Tifton for all 16 rows. And the same thing for Watkinsville, Macon, Midville, everything like that. So that operation to going from a wide data frame to a long data frame in our tidy language is called pivot longer. That's what we're going to do next. So come here on soy K5, give it the assignment symbol. The function is called pivot underscore longer. Remember, always the first thing we give it is a data frame coming in, which is soy K underscore 4. I want to give it a comma and hit return just to make it easier to read. And it has a lot of arguments, and I'm not going to explore all of them now, but the ones that I want to change, the first one is called names underscore 2. This is one of the arguments. So this, we're going to give here the name of the new column where the current column headings are going to go under. You need to give it in quotation marks. I want to call that location.k. So there's going to be a new column called location.k after pivot longer is applied. That's going to have all the current names. So all the current column names. Give it a comma, hit return. There's another argument that I want to change that is called values underscore 2. So this is where we give the new column name where all the values are going to go under. I want to call this, so if you give quotation marks, K underscore PCT. So remember, this is going to be the column that actually has the concentration of potassium on the leaves that right now is spread out in 4 columns. And then lastly, we need to say which columns we want to apply this to. Because you can imagine that we don't want to pivot longer all the columns that we have. We just want to pivot longer the ones that have the location and the values in them. So it has an argument here called cols or columns. We say equals to. So what we could do here is I could use a C function to concatenate and just give all these names, Tifton, Midville, Watkinsville, Macon, inside of this C function. We could do that. That would work. You can try if you want. You don't have to, because I want to show you a way to make this more efficient, perhaps. So let's say that instead of having 4 locations, you had 50 locations. So given 50 column names here would be a lot of work, not efficient. There are many helper functions that allows us to select some columns based on a given condition. I want to show you one here that is very straightforward, I think, and easy to implement. So if you look at these columns that we do want to pivot longer, so Tifton KPCT, Midville KPCT, Watkinsville KPCT, Macon KPCT, they all follow a pattern, right? So the pattern they follow is they have location name as the first part, of this name, and then they all have KPCT at the end of it. And notice as well that no other column that is not related to potassium concentration has KPCT in their name, right? No other column besides these four have KPCT. So we have a K rate here, but no other has KPCT. So there's a function called contains, is one of the helper functions from tidyr, that we just need to give it a pattern that is contained within what we want to pivot longer, and it will just select those columns. So if you come here in contains and we write K underscore PCT, it's going to look for column names that have this contains KPCT in their name and only select them. So we can go ahead and run this. If you got your commas right, if you got your closing parentheses right, it should work. And now if we print soy K5, notice what happened. So first off, first thing to notice is our number of rows increased, right? So we went from 64, we went from 16 to 64, which basically, if you do 16 times 4, because we pivoted longer 4 columns, that gives you 64. That's why our soy K data frame has 64 rows, because we stacked 4 columns below each other. Now, the previous column names that were Tifton, Midville, Watsonville, Macon, are all under this location.k column, because that's what we said right up there of what to do. We also have this new column called KPCT that has all the values that were under those columns previously. Now they're all under one column only that's called KPCT. So notice,
Dr. Bastos,
yes.
I'm sorry, I didn't mean to interrupt you.
Go ahead.
Just a quick question. Let's, like, hypothetically, if like the columns just had the town names and not PCT, is there a way that you could also quickly like select the town names, or would you have to manually type that in?
So your question is, if I want to select these that have this pattern, but then also another column?
No, sir. My question is like if you didn't have, if it was just Tifton Midville instead of Tifton underscore K percent, like could you manually select those specific columns, do you think, or like quickly, or is it, would you have to manually type in each of the columns you want to specifically?
Yeah, that's a good question. So if let's say, so the columns here did not have this pattern of KPCT, right? They just had the column names would be the location names. I mean, you can either then, because they don't have a fixed pattern, because I mean, Tifton, Midville don't really have a pattern, right? Then you would have to either specify manually with the C function. So instead of contains, you would say like C, and then give here Tifton, Midville, and so on, assuming that those were the names of the columns. Or if they are consecutive columns, so here they are consecutive, right? So Tifton, Midville, Watkinsville, Macon. There's no other column in between them. You could have used, let's say, we could have said here, starting in Tifton. So here we could have said, starting in Tifton, and then using the colon notation like we saw for numbers on the intro until Macon. So this would basically unfold starting here, ending here, and everything in between. So we could also do something like that.
Thank you. I was just curious.
Yeah. Thanks for the question. Any other questions or comments here? So I'm showing you these functions in a very specific setting. And my goal here is not that you become a pro at using these functions just by looking at this script. My goal is to expose you to the idea of these functions. So anytime that you're going through your data and you think, oh, I need to make it from wide to long, I know there's a function for that. There are many arguments here. There are many ways that you can do this differently, more complex. And I do appreciate the question. Please feel free if you have any other questions you think are relevant to your case. I will be glad to address them. But I also wanted to just reemphasize that even though we're going through one example here, there are many different ways you can use these and cater them to your situations. For example, this is a great example here. The selection of the columns that you want to pivot longer, there are different ways we can do that. There are different helper functions like the contains function. There are other, like, I don't know, 20 functions that can help you with different patterns. Just to let you know that this is not all there is but the goal is just to expose you to the idea of these functions and what they do. All right, so I'm gonna run soy K, and just looking at it again. So looking again at the new columns, right? So we have location.k and kpct. Kpct is pretty good already for me because it has what it is. It is a K. PCT stands for concentration. So that gives, or for percentage. So that gives us already an indication what it is with the unit of that column. So I'm pretty happy with kpct column as is. However, if I do want to use this location.k in a model, imagine that, we have this extra piece of information here that is kpct, that at this point, we don't need anymore. We need it when it was a column heading because it was telling us what was the measurement and what was the unit of that measurement. But now we just want to know the location. So we really don't need kpct anymore. So next step, I just want to get rid of that. If you go to the next chunk here, there are different ways of doing this in R. There are different approaches. I want to show you one of them. And again, my goal is more to show you the concept of the function, so you'll become aware of it. But we could have done this using different functions in a different way. The way that I want to propose for us to do here is to use this function called separate. So if you come here on the next chunk, give it the assign symbol. Let's call the function separate. As you're already probably thinking, the first argument here is the data frame coming in. That is soy k _ 5. Let's give it a comma and break the code to make it more readable. So the first thing that this function takes is what is the column that you want to separate. So what I want to separate here is basically Tifton from everything else. So these values here, they're all under this column called location.k. So we can come here and say the column name that we want to separate is called location.k. I want to give it a comma, hit return again, and it has another argument called into. So notice how if we just look into one of the values here, they all follow the following pattern. They have location name first, separated using an underscore from K, which is separated using an underscore from PCT. So if we just say that we want to separate this column, R is going to look into these values and is going to realize there is only one common separator, which is underscore. If we had underscore and then space, you would have seen two separators, and then you would have to be more specific of which one of them you want to use to break that string. In our case, because it is the same consistent separator that is underscore, separating three pieces of, or three words here in these values, R is going to go, separate is going to go into that column, find those two underscores, and it's going to remove them, and each one of those pieces will become a new column. Because we have three pieces, we have to give three new column names that where those pieces will go under. And we do that through this argument called into. So I want to say into, let's use the C function because we're going to give three values here. The first one in quotation marks, I want to call location. Then you give it a comma. The second one in quotation marks is going to be called K, comma. The third one in quotation marks is going to be called PCT. So it's going to create three new columns, location, K, and PCT, where all the location names will go under the first column. K is going to go under the K column, and PCT under the PCT column. These names here, there's nothing special about them. It's just what I wanted to call them. You could have chosen different names. You could even just call it ABC if you wanted. Of course, that is not very intuitive if you're just reading the code, but just wanted to make you aware of that. So if you run soy K6 and you print it, now notice that we have this location column where all the location names are under, this K column that basically is all K all the way down. There's really no information for us to really use here, and the PCT column where the PCT piece fell under. I want to call your attention here for one thing. If you, let's say you have, the best way for you out in the field is to collect data like this. You go to Watkinsville, you collect data for that, and then you take the same sheet, you go to Midville, collect again. So your data collection process is easier on an untidy format. That's fine, right? We don't have to collect things in a tidy format, but we need to learn how to make it tidy afterwards, which is what we're doing here. And if that's the case, whenever you're collecting data in this way, so especially if you have information that's needed for you in the column headings, like we just had here, it makes your life easier if whenever you're typing that data into your computer, you're already thinking of using common separator characters like underscore, or even, you know, a dash wouldn't quite work here. I would say underscore is probably the best one. But let's say if you had a different piece of information here that you wanted, you know, you wanted to have, instead of Tifton underscore K underscore PCT, you wanted to have, you know, Tifton underscore K dot PCT. Then you could come here and say separate using underscore. It would create two columns for you, Tifton and K dot PCT, because the separator was underscore. And then, you know, just be thinking about these ways of how you can make your life easier when you actually get to wrangle and analyze your data. So using separators that make sense for you. That makes it easier to separate later, I guess, is the message I'm trying to convey. Okay, so we
Dr.
separated.
Bastos, my code looks the exact same as yours, but I'm getting an error.
Do you want to share your screen?
Sure can.
Okay, let me just stop my sharing and allow you to share.
Sorry for this.
No, you're good. All right, you should be able to.
Tell me if you can see it.
Okay, I can already see what's going on. Let me zoom in and help those here in Athens. Okay, you know, this is great because really when you're coding, you're going to run into issues for sure. So I do appreciate opportunities for us to troubleshoot together. I want to ask, I mean, anyone really, if you can help Austin here. Okay, so I had a lot of people here in Athens saying the spelling of the function. So, you know, let's just go through. Yeah, Kriti also said in the chat, separate. So you have the spelling of the function wrong. You need to replace the E after that P by an A. Yep, and that should work. Yep, there we go.
Sounds about right for me. Thank you so much.
Yeah, no worries. And this is really a good exercise because, you know, it doesn't happen always, but sometimes the error messages are useful, right? Sometimes they make no sense and it's really hard to really understand what they're trying to tell you. But in this case, I think it was useful. So just to reproduce your error, you had separate. So, you know, if we look at the error message, it is saying could not find function separate. So that error, even though it's not telling you exactly what's going on, but it should set you in the right direction of like, okay, separate. Where did I type that? You know, and why is it not finding that? In this case, it was a typo, right? But you know, that can give you some hints of how to troubleshoot. Awesome. Anyone else having any issues that you need help with? No? Okay. All right. So let's keep going. So, so right now, Soy K6 has 64 rows, 10 columns. And notice how some of these columns are really not very useful. So plot number, we don't really need that for an analysis. Treatment number, if we only had treatment number as the only treatment column or the only column identifying treatment, we would need it. But we actually have potassium rate both in pounds per acre and kilograms per hectare, which treatment 1 is all 0 pounds per acre, treatment 2 is all 50 and so on. So really, if we have one of the potassium rate columns, we don't need the treatment column here anymore. Stage is all a single value, is all R4. So really there's no information for us to use in the model related to that column. So it's also really not that useful. If I wanted to continue my analysis using, oh, wait, am I sharing my screen online? Okay.
Yes.
Yeah.
Thanks. So if I really want to run some analysis, I would need to have at least one of the potassium rates column. I would need to have the rep column, that's my block. I need to have the location. I do not need K, I do not need PCT, but I need the K PCT column with the actual concentration values. So next up here is a function that I use a lot that is used to select columns. So if you think about it, filter is applied to rows, right? So I'm only filtering the rows that have a given value, let's say potassium rate equals to 0. Select applies a similar concept, but to columns. I only want to keep certain columns in this data set. So let's go here on the next chunk on the soy K7, and let's just select the columns we're going to be using just to make our data set a little bit more, clean, I guess, and only have what we need and not a lot of extra columns we don't need. So we come here on soy K7, give it the assignment symbol. There is a function called select. And notice how it is coming from the dplyr package here. I want to just take one moment here and tell you that the function select, the name of a function select is a very popular name across many packages. So what happened to me a lot of times, and I've seen online other people reporting this as well, is you're doing your data wrangling and you're going to select some columns. Your syntax is correct. Everything is correct, but it's giving you an error that makes no sense. You're like, this doesn't even seem like it's doing what I wanted it to do. And that happens especially with the function select, because again, it is a popular function name across packages. So there's a package called raster, which we're going to be using, no, maybe not in this class. We're going to be using in the PrecisionNet class. But it is a package that deals with raster data that also has a function called select. And if you, in the same script, load both of the dplyr and the raster package, depending the order that you run them, it may be that the select function that you use by default here is coming from raster package, which does not do what the dplyr one does for us. And then it's going to give you an error again that makes no sense. Until you realize what's going on, it takes some time away from your productive day. So to avoid that, I want to show you one way of avoiding this. There may be other ways, but one way to avoid this is to explicitly call what package I want this function to be coming from in this specific case. So to do that, you would type the package name, which is dplyr. So the select that I want to use coming from dplyr, and then you use the : notation. So this is saying I want the select function from the dplyr package. This is not going to be an issue for this script here, but I do want to make you aware. And it's not an advice I'm giving just like for every single function you use. It is very specific to the select function, again, because that's a popular name of functions across different packages that have different functionalities. All right, so now that we're using select function coming from the dplyr package, as you may be thinking, the first thing here is the data frame coming in. So that is soyk_6. And then I just want to give a comma and hit return to make it more readable. And we can just give here the name of the columns that we want to keep, right? So I'm just going to print the names of soyk6 again, just so we can see it below here. And we can do this exercise. So I want to bring location. That's going to be important. We do not need to give quotation marks here, although I think if you give, it's not going to hurt, but then you're going to have to put that in a C function. So let's just give location. We do need to have the treatment rate. I want to keep the kilograms per hectare since that is the international unit that we're going to be using further. Give it a comma. I do want to keep here the rep. That's our block number. We're going to use that for modeling. And then lastly, we need to have the actual trifoliate potassium concentrations. That's under the KPCT column. So if you do this and you run that, the product should be this data frame here that has still 64 rows, but now we're just keeping the columns that make sense to you, that are location, potassium rate, kilograms per hectare, the rep or block number, and then the KPCT. All right. So just a quick refresher here, filter function applies to rows, select function applies to columns. All right, the next one I want to show you here, if you come on the next chunk, is the function arrange. So arrange is basically a function that we use to sort values according to a given column. It's not going to change really your data in a way that affects analysis or plotting, but it's just more if you're printing your data and you want to see all the, let's say, the mid-view locations first, they would be all grouped together if we do that. So just want to show you how to do that. If you come on soyk_8, give it the assignment symbol. The name of the function is arrange. we need to bring that soy k_7 object. And then you need to say what column you want to arrange by. So I want to do location to have locations all printing together, or all observations within a location printing together. So as we do that, we see that it basically arranged the location column alphabetically. So it is Macon, Midville, Tifton, and Watkinsville. We could have chosen a different column, and even more than one column. So if I wanted to have all of the reps together for some reason, I could say rep. Remember that location is a character column, rep is a numerical column. That does not matter. If it is character, it would be alphabetically sorted. If it is numerical, we would be from lowest to highest. As we see here, all the reps won across all different locations grouped together. And also, it always does from A to Z, from lower to higher. If I want the inverse of that, or the descending order, there is a function that we can use here that's just desc for descending. Make sure you close your parentheses at the end, because then you're closing one for the desc function, one for the arrange function. If you run that, now all reps for rep number 4 are going to appear first. Right? So I'm just going to delete this and just leave location, but I wanted to show you a few variants of that. All right, so the next step here, and I think it may be, yeah, the last one of the actual wrangling exercise is at some point, I am sure you're gonna have to be calculating mean, standard errors, minimum, maximum, very statistical summary values for your data. And I wanna show you how to do that very easily here in dplyr. So let's come to this next object here called soy k9. I want to give it the assignment symbol and use the function group by. So let's say I want to know the mean potassium concentration for each location. So basically averaging across treatment, averaging across reps. I just want to know one value, the average value for each location. This is where we say, what is our grouping variable, right? So I want to group by, we have a column called location. So I just say location here. That's this column right here. So it's basically creating groups based on that column or the levels under that column, right? So if we run this group by, I had an issue. What's going on? Group by. Oh,
The data.
yes.
There we go.
Nice. Thanks, everyone. I'm glad that you're paying attention here. Yeah, so the data coming in is soy K8, right? Just to confirm, the previous one was soy K8. I need to give it a data frame first. Yes. So data frame there, and then the variable that we want to group by. So if we run that and you print it, what you're going to notice is we still have 64 rows, right? And if we're doing a summary of something, we should have less rows. We should be expecting to have only 4 rows, 1 for each location with the mean. What's happening here is that we set up the grouping structure, but we have not told it yet of what we want to do with that grouping structure, right? So group by creates you that grouping behind the scenes, and then is waiting for the next step for you to tell it what to do with that grouping, right? Another way to look at this is, so soy K8, the one that we're using here before the group by, if we just explore the class or the type of that object, as we already talked about this function class here to explore the type of an object or a column inside of an object, it is a tibble data frame, a tibble, and a data frame type. Now, if we check the class of soy K9, it is all that as well, but it is also a grouped data frame. And now if I print soy K9 again, notice how it says here that it has groups based on location, and it has four groups, I guess. Right, so it's just for you to remember that group by itself only creates that structure behind the scenes, but now you need to come back and tell it what to do with that structure. That's what we're going to be doing here with soy K10. So if you give it the assignment symbol, the function that normally we call after a group by, so a pair of functions that are used together is group by and then summarize. So if we call summarize, we need to give it the grouped data frame. So that is soy K9. I want to give it a comma and break the line just to read better. I want to create a column that I want to call mean K underscore PCT. I give it an equal sign, and this is where I give the actual summarizing function that I want to use. The function here is very intuitive, it's called mean. And then you just say mean of what? So what is the column that you're trying to get the mean of in this case? If I'm trying to get the mean of the trifoliate potassium concentration, what column should I say here? Which one? K underscore PCT. Yes, right? Because those are the values I want the mean of. So K underscore PCT. If we run this object and print it, now it is actually what we are looking for, right? So we want the average, which is a single value for each one of the locations. A couple of reminders here. If under the KPCT column, we had even just a single NA value, these means will return NA. Remember, every time you use statistical summary functions like mean, median, minimum, maximum, standard deviation, coefficient of variation, maybe others I'm not remembering, it has this default of na.rm equals to false. So it does not remove NA before doing the calculation, which gives you an NA if there is an NA in that column. It was not the case here, but if it would have been the case, you would have just said na.rm equals to true, changing that default behavior to actually remove NAs first. This would give the same result for us since we don't have any NAs, so I'm just going to delete this, but I wanted to remind you of that. Also, this summarizing function here could have been a different one, right? As we said, it could have been median, minimum, maximum, CV, SD, and others. I'm just showing you the mean here, just so you have an idea of how to get a summary. Let's see, what else? Oh, I just want to show you something here. So the summarize function does not need the group by function. So I've used sometimes the summarize function by itself without being preceded by group by. However, let's just try that. So the object that was not grouped by was called soy K8. The one that was grouped by was soy K9. If I just change here the data to soy K8 and I run this, I get one single value because now it applies that summary to the entire data set because it did not give it any structure behind it, any groups behind the scenes, right? So I just wanted to show you what would happen, but I just want to come here and make sure that you change this to soy K9 because I do want those groupings. I do want to know the mean by location. Okay, so the next step here, I think is one that is really interesting. My efficiency of programming in R really changed, and even the style of my coding in R changed after I learned this next tip and tool. If you notice, right, so let's just quickly take a look here. We started with soy K, right? So when we read the data, so we brought in a data set called soy K. Then we apply clean names, applied filter, even though we did not keep the soy K2 in the flow, but we applied a filter function. We applied a mutate to transform it to international units. We created the reps using the case when and the mutate. We made this longer data set to get location information using pivot longer. We did a separate to separate that information on the location. Then we selected on the columns we wanted. We arranged by a column. We did a group by and a summarize. All these steps, all these functions are functions I use very commonly in any data wrangling exercise, which is basically any data analysis I do, because very rarely you have a data that comes in ready to go. You normally have to do some wrangling, and this is what I mean by wrangling. If you notice here, each step, what we were doing is bringing in a data frame from the previous step, using a function, assigning that to an object. Then going to the next step, again, bringing the previous step, doing something assigned to an object, and so on, right? So here we basically created 10 intermediary objects that we really don't care for. Let's say if my goal is to get to this table here, this soy K10 is the object I want. I don't care about all the previous ones, but we had to create them so we would be saving step by step of what was happening so we could use in the next step, right? This is very common in programming to do things step by step. And normally there are two ways you can do this before I show you a better way. One is doing what we're doing, creating multiple intermediary steps and just creating a lot of objects in your environment that you really don't care for. The other way, which I think is even worse, would be to be nesting all these functions one into the other. So let's say you would have one piece of code where you have, you know, clean names inside, and then or I mean, if we just follow here, so it would be a clean names inside of a filter, inside of a mutate, inside of a case when, inside of. As you can see, it gets really, you can do it, it would work, but it does not look nice. It does not look intuitive when you read that code. And that's the one thing we're going for here is code that is intuitive, you understand what's going on. So the solution for that, if you come here on the piping it all together, is to use a pipe. So what is a pipe and what does it do? I want to come outside of the chunk here and type something just so you can see it. When the pipe was introduced through a package to the R community, the pipe is this symbol here. So it's percent greater than percent. So what it does is takes what is on its left side and feeds that as the input, the data input of whatever it is on its right side. So here, let's say I have a data frame called A and I have a function called B. The pipe would take A and place it right here as the first argument as the data frame of the B function. But you don't have to say the A here on the B function, because that's what the pipe is doing for you. So you do not even need to specify that A is coming to be in the B function because pipe is doing that for you. This became such a popular way of programming in R across different people. A lot of people started taking up this style that it was first introduced as a package. So someone produced a package, made this available. A lot of people started using it. It became super popular. That the developers of R itself, so not a package, but developers of R decided to incorporate the pipe concept into R itself in a way that you don't even need a package for that anymore. It already ships with R. And I'm telling you that because I started using the pipe when it was coming from a package. So I use this notation here of percent greater than percent. But if you, the pipe that ships with R already is the same concept, but it is a slightly different symbol. So it is the vertical bar greater than. This would be the pipe that ships with R. Right, so it would be A pipe B function. You can use them interchangeably. If you have a preference, feel free to use whatever you wish. I don't really care, but I'm just telling you this because, you know, as you're Googling for help, or you're looking at Stack Overflow, ChatGPT, whatever it is, you may see one of these two pipe types. And I just want to let you know, they basically do, as far as we're concerned, they're the same. It's just that one comes from a package, the other one comes from R already. Okay, so what I want to ask you here is that for us to connect all these steps in a pipe workflow. So to do that, let's start with this object called soyk_w. This is really the convention that I do on my own scripts is I bring in data, so let's say soyk, and then I have a next chunk that I use just for wrangling, and I create whatever I do there, I assign to an object that ends with _w to mean to me that version is the wrangled version ready to go. So this is what I do. So we give it an assignment symbol there. We're going to start off with the soyk object, as that is the first step, right, was to read that Excel and bring into a soyk object. We give it a pipe here, and the convention is that you would hit return after a pipe. So you break your code and make it even more readable. Now, it's going to be, to do what I'm going to do next, is going to be important that you can see your outline. If you're not seeing your outline, there is an outline button there. You can just toggle that on and off. You should see your outline if you toggle that on. On the first class, we went through the steps of making sure your named chunks appear on your outline. If you are not seeing your named chunks here, which you will need to do what we're going to do next, it's because you did not do that setting that we went through in the intro. And you know, I just want to ask here, is anyone not seeing your name chunk? So soyk 1, 2, 3 in your outline. And it's okay for not seeing, you could just raise your hand. We're gonna go through how to fix that very quickly, because if you're not seeing, you need to see it. Okay. I don't hear anyone. I don't see any hands up. I'm gonna assume you're all seeing this outline that I'm seeing as well. If you're not, again, instructions to be able to see your outline are in the intro script. Okay, so we're starting with soyk. I want you to come to the first object we created. So soyk1, let's just come there. And I want you to copy what's on the right-hand side of your assignment symbol. So just the clean name soyk. Copy that. Go back to the piping it all together chunk and paste it below that pipe. One thing here is that because the pipe is already placing the soyk in here, we do not need to say it again. So you just go ahead and delete the object name from clean names, and you should be seeing this. If you run this piece of code and you print soykw, that is exactly of what your soyk1 is. Now, the difference is that we're going to be further developing this flow by adding each one of the functions. So what we do next is we come here, give it another pipe, hit return. Now I want you to skip soyk2. As you remember, we did not use soyk2 in our flow afterwards. I want you to come to soyk3 on that mutate. Again, copy everything on the right-hand side of the assignment symbol. Go back to the piping it all chunk and paste it right below clean names. Again, a reminder is that you do not need to specify what's coming in. So go ahead and delete that soyk1 and the comma after it. So we're going to be doing this until, I believe, soyk8. So I'm going to narrate the first few ones here. I want you to do this same thing on your side, where we add a pipe, hit return. Now the next one is going to be the soyk4, where we did a mutate in case went together. So I copy that, go back to piping it all together. Right after that pipe, I pasted, and remember to remove the data frame coming in, because now we don't need that anymore. I go after the last parentheses here of that mutate, add a pipe, hit return. Now I go back to soyk5. That's where we did pivot longer. Copy that. I go back to the piping it all together chunk, paste it after the pipe, remove the data frame soyk4 and the comma after it. Go to the end of that function, add a pipe. Now we go to soyk6. That's the separate. Copy that. Go back to piping it all, paste it, delete the dataset name. We're going to keep doing this for a few more steps. So add a pipe. Now we go to the soyk7 where we did the select. Copy what's on the right-hand side of the assignment symbol. Go back to piping it all together. Paste it there. Delete the dataset name. I think we have one more step. So add the pipe. Go back to soyk8 where we use the arrange function. Copy that. Go back to piping it all together. Paste it here. Remove the data set name. Okay, so if you did it all together, or I'm sorry, if you did it all correctly, which involves adding the pipe, making sure you remove the data set coming in from all the functions that we copied and pasted, and you follow the steps as we did. So we starting on soyk1, skip soyk2, and go all the way to soyk8. So we're leaving group by and summarize out of this pipe workflow. So if you run until here, and you run all that, you should have gotten a green light. It should not have given you any issues. If it did give an issue again, the first things I would check is make sure you have the pipes in the right places. Make sure you remove the dataset names from all the functions, and that should fix it. Now, if you print soyk, it looks very much so like soy K, or I mean, soy KW looks very much so like soy K8. To check for that, you just need to change one thing here. So we went all the way through a range. So there's a function called identical that it basically compares two data frames, and if they are 100% the same, so every column, every row, every cell of the table is exactly the same, this comes back as true. If there is at least one little thing different, it comes back as false. So if you compare soy K8 with soy KW, it should come back as true, meaning they're exactly the same. Before I keep moving, I just want to ask, was everyone able to make your flow work? Or maybe let me ask differently. If you were not able to make your pipe flow work, let me know and I can help you. So really, when I do data wrangling, I would basically bring in soy K, and this would be my immediate next chunk. I would never have all the intermediate steps here. I showed you them to show you how, I guess, you would have done if you did not have the pipes, and also to show you how the pipes really help you to think through what you're doing with your data. Because all these functions, they have names that are very intuitive of what they're doing. Most of them are verbs, which is one of the philosophies behind tidyverse packages, is their functions, most of them are verbs. So it's really easy for you to understand what is going on just by looking at that function name. And really when I'm thinking I guess the more data wrangling you do, of course, the better at it you're gonna get. But it gets to a point where I look at a data set and I'm already like, okay, I have to do a pivot longer, and then I have to filter here, maybe I have to create a new column, maybe I have to do this, this, and that. And just in your head, you already know what you have to do. And then it's easy to translate that step by step in a pipe workflow by thinking what you need to do, and then translating that into functions that then you apply using programming. All right, any questions or issues or anything? All right, I don't hear anything. So the next step here is let's save. So why am I showing you this? Is because you will be doing data wrangling for every single project that you have, for sure. Sometimes, it's a very simple data wrangling. Sometimes it's more complex, but some data wrangling always is needed. And what I started doing was, in the beginning, what I would do is I would have a data wrangling script like this, and I would right off the bat, right here, start modeling. I, with time, realized that's not a very efficient way of working, because then you have a script that does a lot of things, and if you have to change something, it becomes more difficult. So then I started breaking down my code into components of an analysis. So this would be the script that I use to bring in data, wrangle that data, and then I export this data to file as a CSV, for example. And then that CSV is what I bring into my next script where I'm doing some analysis. So then you kind of compartmentalize a little bit better your objectives of a given analysis. And I want to show you how I would do here in this case. So, we got to this point here where soy KW is our data that we want to use further. So let's export this to file. So next time I need to use this, I don't have to rerun this script again. I can just simply read that soy KW from file into the next script. Yes, Osman?
I have a question. So I was listening, I was letting the data to that function, but after that, when we did checking, the result is same. So it is coming like I got false.
You got false? Okay, so the first thing I would say is, I think the code I sent you had soy K7 as the comparison. Please go, if you have that, change that to 8.
Yeah,
Okay, so you have soy K8 and you have soy KW.
Yeah.
So,
I don't have soy K.
oh, you don't have soy KW. Okay, so that's the reason. So soy KW is what we created above here. So this is the soy KW object that we basically did all the pipe workflow. So that's the one that we want to compare to. At least we're able to see what's going on. For those online, we're just troubleshooting a little bit of code here in person. Just hold on a sec.
Extra pipe.
Yeah. Oh, yeah, yeah. That's yeah, so there was an extra pipe at the end. I just want to show you this to you all. If you add a pipe here and you don't do anything else, R is expecting something to come after this pipe. So if you leave a pipe that is not followed by a function, it's gonna give an error, right? So if you do this, yeah, it is right there. So in this case, the error is not very intuitive, right? It's not telling me there is an extra pipe here. But I can tell you that that's what's going on. So you don't want to have your pipes just lingering there without a function to be followed. In this case, if you just remove that, it would work. Okay, so coming back here to what we were talking about, exporting this data set as the clean wrangled version, ready to be plotted, analyzed, and so on. We want to save this to file to use this in the next script. I want to save this as a CSV file. For that, we're going to use a function called write_CSV. I want you to call your attention that whenever we're reading file, so something that's on file, I want to read into R, we normally use a function called read_ or maybe read dot something. That something is normally related to the extension of that file. So if you recall, we used read_Excel to read the data, right? Now I want to export data. I need to use a write function. And because I'm telling you I want to export this as a comma separated value type of file, a CSV file, we use write_CSV. So the first thing we give it is the object name that we want to export. So that's soyk_w. Give it a comma, hit return. Now we need to say where to export this to. Whenever we're working with paths, I want to say specify a given path. I need to use the open and close quotation marks. And it's the same concept as we talked about when we're reading data. If you have your cursor blinking in between the quotation marks and you hit tab, for me, it shows 3 files, and I know these files are inside the code folder. For you, it may have already filled for you like that because you may have only 1 file in this folder, so we already filled that for you. Please delete this because I did that just so you could see how to use tab to see where you are. Now, I know that I want to export this to a different folder. In this case, I'm proposing we export to the output folder. It could have been also to the data folder. Some people do one or the other. I just want to propose we export this to the output folder. So to do that, if you remember, we have to get first outside of the code folder. For that, we do .. to get 1 level up. Now you hit tab. This shows you where you are. So we see that we are in the main folder of the project. I go inside the output folder. And now because I am creating something new, if I hit tab, there's nothing's really gonna happen. Or maybe I guess you shouldn't hit tab once you get to the folder you want to export. Now we just give it a name. So I want to call this soybean_processed. And then besides the name, here's also where you give the extension. So let's say .csv. So if you run this, it's not going to tell you anything unless you have an error in your code, then it's going to yell at you. But if it worked, it's not going to tell you anything. But you can make sure that it worked by coming here on your Files tab, clicking on that R blue button to go back to the main folder of this project, and then go to the output folder. You should see now the soybean_process.csv there. So now the next script that, if we were to immediately in the next script be analyzing this data, we would simply read in soybean process instead of reading the Excel file and doing all the wrangling again. Okay, so I have an assignment for you that is not going to be done in class. You can submit this to me until right before next class. What I want you to do is starting with soyk, and I already left you the chunk here for you to work with that. I want you to use data wrangling functions in a pipe workflow to generate the average potassium concentration for each potassium rate in kilograms per hectare within each location. And a tip is that this data frame should have 16 rows at the end. So again, if you just read this sentence here, especially going through the exercise we just went, you should be already reading things here and be thinking, okay, I need to do this, that, and that, and that, and these are the functions that connect to the actions I have to do. So I want you to do this, using this in a pipe workflow. I want you to submit that to me. And to submit your assignment, you can just email me. This date here is wrong, so you can disconsider that. This would be by Tuesday, January 23rd. But then it's right before class, so it would be not 11:59. This would be 9:30 a.m. Okay, so I just need a screenshot. You can send me by email by your final data frame. So let's say if your final data frame was this is what the screenshot you would send me, but it's not this, right? Because it's a different setup. So this is what, this is the assignment that I have for you. And okay, 10:52. Let's do this. I have not done a quiz through ELC that I applied to class yet. I attempted to do one today, and I want to see how that goes. So let me come to my ELC. I think it is available. So if you go on your ELC for this class, I guess I'm going to get some feedback from you because I think I did it right, but maybe I did not do it right. But so come on this class on ELC. And there's going to be, I think if you come under, well, maybe you see differently than, I mean, your view is different than mine. But I published a quiz that should be active. No quiz is active. Okay, let me try to, maybe I have to change. Okay. So maybe now is active. Try to see if that is active. It's a very simple, easy quiz. Just to see if you're, following the concepts. Is about tidy data. So it's mostly related to some of the things we talked about, but also if you read the tidy data paper from Hallie Wickham, I'm sure you're going to be able to answer these correctly. So just click on the ones that you think.
Still not able to get in, Dr. Bastos.
Sorry, what was that? Can you repeat that?
I don't, maybe it's just me, but I'm still not able to get into the quiz.
Okay, I think,
I don't know if anyone else is able to get in.
yeah, maybe if you refresh, I think here in Athens, people were able to. Yeah. Yeah, so maybe if you just refresh the page, that should become available. Awesome. I'm just going to give you here a couple minutes. It's a very easy, straightforward quiz. So not a lot of time required for completing that. Give you one more minute here. So 10:55, we'll come back. All right, so let's keep going here. You know, if you have not finished yet, please do so. The quiz is gonna close, I think, right before the class ends. So it's wise if you just go ahead and do it now. Don't worry if you don't remember, you know, this is just so I get a feeling of how you're thinking through some of the concepts we're talking about. And even though quizzes are worth your part of a grade, but again, I'm more interested in seeing what you're thinking and maybe where I am not being clear, or maybe, you know, I should spend some more time in different topics. This is just a way for me to gauge that. Okay, so if you, the next immediate step here of our class is going to be to go through a lecture on GitHub. I think we're going to be able to get through the lecture. I don't think we're going to be able to get through the actual hands-on part where you install things and we check that things are working. That may have to be for the next class period. But I have a lecture that I posted here if you want to follow that along. You already know how to download a lecture as PDF if you need to. If you don't remember, there are instructions in the first lecture, the intro lecture, on how to do that. All right, so Git and GitHub. You know, I just have this acknowledgement here that some parts of this presentation were based on these slides. So this is, if you followed the presentation on the website, this is a hyperlink that takes you to a presentation from Dr. Mina Setinkwaya-Rundle. If you're not familiar with this name, it would probably be useful for you to be. So Dr. Mina is a professor at Duke University, so just north of us, a couple of states at North Carolina. And she's so she works for the stats department at Duke University, and she's also a researcher at our studio. And she develops a lot of the teaching material that I either use or refer to, or that you're gonna see online in different ways. Just wanted to make you familiar with that name. All right, so the goals of this presentation here are to talk about a little bit about what is Git, what is versioning, how do we work locally with Git, and then get into the GitHub side of things. So what is GitHub? How do we work both locally but also remotely on, and what workflows we use for that to combine both Git and GitHub? And then we're going to set up Git and GitHub workflows in our studio and some tips and resources that I have for you. All right, so to begin with, what is Git, right? So we talked a little bit about this, but you can think of Git. So Git is a version control software that you can kind of think of it as track changes, but really not just, doesn't apply just to Word files, but can really, I mean, is really actually not even that useful for Word files itself, but it's really useful for code. So keeping track of changes in code, so you know exactly what changed from one version to the next, who made those changes, where are those changes in your script, and so on. And it is not the only version control system, but it's probably the most popular and used one. So that's why we're going to be talking about Git and using it in this class. So Git is very useful for versioning. So let's say this is a quick example of building a Lego house, right? So we see here where we're starting at the first version, then we put some bricks there, we keep building it all the way until the 12th version here, where we have a full house. Kind of think of this concept, but on your own code. So you start very simple with your code. Maybe you just have a chunk, maybe you import data. Then tomorrow you come in and do some data wrangling. You realize it's not enough. The next day you come in and finish it. And then you come and then do an analysis and so on. So this is what versioning is about. Is the main difference here is that between each one of these versions, we're taking a snapshot of what happened. So I know exactly the difference between V1 and V2, or even V1 and V12 if I want to, right? I know exactly what happened in each one of these steps because of version control. It is keeping track of that for us and helps us to go back in time if you have to. So we talked a little bit about this, right? I mean, I want to revert back to version V9, and because I got to V12 and it was stuck, I remember V9 was working. Let me go back to that and rebuild again. We can do that with version control very easily. And then versioning using Git is really one of the things that Git has is this concept of a commit. So a Git commit is basically you taking a snapshot of your files at that point in time. So Whenever we also do a commit, we do that in a way that we provide a message of what was done. So let's say your first commit here, the message is first commit, and then the second commit, it says build back in front of the base. The third one is finish building base, and so on. So you add a short yet descriptive sentence to remind your future self of what happened in that new Git commit that you did in that snapshot of your files in time that you just did. If you have never worked with Git, I guess let me tell you one thing before I show you a common workflow to work locally. I'm going to show you here a very simple workflow. This lecture and in this class, the goal is not to make you a pro on Git or GitHub. That's not my goal. There's a lot of things I don't even know how to do in GitHub, and I don't expect you to know. If you do know, great for you. You can use it. It can be, even more productive or creative with your skills. In this class, I want to teach you a simple workflow that works for me and works for most people most of the time. So how would that look like in your computer? After you have already installed Git, so if you have a Mac or a Linux, that I believe ships by default in Macs, I'm sure it does. In Linux, I think it does as well. If you have Windows, you have to install Git Bash, which there are some instructions in that ebook that I share with you as a reading material for this class. So after already having installed Git, assuming you have already installed in your computer, you would basically go to your terminal or your command line and go to that folder and start a Git project by using the command git init to initiate a Git project. After it does that, Git creates some files for you that kind of keeps hidden, so you don't really see much of what's going on if you just look at the folder. But then you can really start creating your folders, creating files, modifying those files. Whenever you're ready to take a snapshot. So let's say you started a new script that you did import data and you did some data wrangling. Now you want to take a snapshot of that in time. Before we commit or before we take that snapshot, we first have to stage those files. So it's almost like you're taking these files that made changes and you're telling it, here, these are the files I want to commit. And we do that by saying stage. And then after we stage, that's when we commit. That gives you the option of only committing changes or taking a snapshot of the changes in certain files, because you have all these files in your workflow. Maybe you just want to commit the changes in the script file. Maybe you don't care about committing the changes in the data file if you did pay changes there. And Git stage allows you to do that because you can say just stage this one file and not all these 10 files I have in this folder, and then you commit those changes. I normally stage everything, so I'm keeping track of all my files, and that's why I use this flag -A that stages all files that I potentially made changes since my last commit. So you would stage your files, and then you would commit your changes by using a git commit change. We use this flag -M to give it a message, so a commit message that we give that message within quotation marks, and we just give something that is short but informative related to the changes that we just made since your last commit. This would be a very common, easy, straightforward workflow that most people using Git locally would do. And then, so let's say today you come and you do some changes. You develop part of the script for the wrangling exercise, and you're done for today. So you commit that change. You say, did a few wrangling functions, still need to work on this tomorrow. That's your commit message. Then tomorrow you come, you continue that script, you build more of that script, and you finish your wrangling. Now you git stage, git commit, and then you can say finish wrangled steps. So every time you come back and do something new, you would be committing or be staging and committing, staging and committing. Remember, stage and commit are the dual functions that take that snapshot for you. So each one of these versions that we saw before were stage and commit, stage commit, stage commit, and so on. One recommendation is that once you finish an important step of your analysis, I guess, overall, you do a stage commit. You want to be able to think, okay, I want to go back to right before I wrangled. you have a commit there. I want to go back right before I started analyzing, you have a commit there. So you have these like timestamps over time of points of your workflow that you can go back to if you have to. So if I start my script, develop everything from beginning to end and commit only at the end, it's not very useful because I don't have timestamps in between. I don't have commits in between that allows me to break more down that time series. So I really want to commit often. So the way it works here is, let's say you have a working directory, right? And you change some files. You first stage them. You can think of them in this staging area where Git is looking at to see only those files, what and how have changed in them. Then do a git commit. Those are your committed files. So now any changes from your last commit to the current one are packed into this commit. And we haven't talked yet about yet in this presentation about how to use GitHub, but once you do those changes, so make a change, stage, commit. This is all locally in your computer. And then for you to upload this to GitHub, once we connect your local and your GitHub page, we do a git push. So that pushes your changes up to GitHub. Kind of think of uploading your changes to GitHub. So maybe, you do a git push and then you go work on a different computer. You can go on your GitHub repo online, download a copy of the repository if you want to, keep working straight off where you left off on a different computer. Of course, there are different ways of doing this, but this would be one of the ways you can do this. And then let's say you are working with someone else in a project, and they also have a same version of this project in their computer, and they made some changes that they git stage and get commits locally, push the changes to GitHub, but you don't have yet those changes on your local version. So on your computer, you would say a git pull, which basically downloads those changes from the GitHub to your repo and incorporates them already for you. So you're all working off of the same version. Okay, so we talked about Git. Now, what is GitHub? So GitHub is the home for your Git-based projects on the internet. So almost like OneDrive, Dropbox, but much better because it doesn't only store your files, but also keeps a history of your commits, right? And that's, again, the strength of Git. So we're going to be using GitHub as a platform for web hosting and collaboration, and also as your course management system. So what I mean by that is from the point after everyone set up with getting GitHub and they have a working version of them, we know what to do, how that's going to work. Everything that we do in this class is going to be you're going to have a local copy of what you're doing, a personal local copy of what you're doing, but I also want you to have a copy of that on your own GitHub page where each project is going to be a repo on your page. So we're going to be making changes like we did today, right? So if we were already doing this, by the end of the exercise today, I would have done a git stage, git commit, and git push. And I would go on my GitHub page. I would see all the changes I made today already there. And I just want you to have that habit, I guess, in this course. We're going to do that a lot. So how does it work so remember, Git is on your computer, that's locally. GitHub is what is like Dropbox for Git projects. So there are a few different ways of working together local and remotely on GitHub. So one of them here, I'm not sure if you can see, but this is basically GitHub. This has it's representing GitHub, this square here. It has this sub box here called dem, which imagine that this would be a repository where someone else owns it. And then have another box called you. So you can think of that as a repository that you own, that you have control of. So one of the ways of working, I guess in this case of not working with GitHub, is having your files and projects managed locally with Git, but never connecting that to GitHub. A lot of people do this. This works as well. You get the Git benefits. You do not get the GitHub added benefits of collaboration and having what you're doing, hosted somewhere that can be shared as well. A very common workflow that's going to be the one that you are going to be using most of the time in this class is what's called a GitHub clone, where you own the repository. So let's say you're going to have on your own page, you're gonna have a repository for each one of the projects, and that is synced with your local version, with what you have on your computer. This is what we're gonna be using most of the time in this class, just so you're aware. But there's others. So another option here would be a GitHub clone. So it's also a clone, but someone else owns it and you are a collaborator of that project. So let's say I go there and I create a project, a GitHub repo that I bring to my computer. I do changes locally and I push those changes to GitHub. But I invite you to be my collaborators. So you also have access to that repository on your computers and is also synced to GitHub. So I own it, but you have the rights to make changes locally and to make those changes appear on GitHub on this project. That's what this workflow here would be. We may use this for some assignments. I'm still thinking of how to incorporate this, but I think we're going to have some group assignments where you're all going to be working through GitHub together in the same repository. So this is going to happen at some point in this class, but the most common one that you're always going to be using is going to be number 2. And lastly, the last workflow I want to show you is a GitHub fork and clone. What does that even mean? So a fork and clone is when someone else has a project, so it's not on your repository, but you want to have a copy of that locally. You can do that. We can go on any software. If you see Google, Facebook, Amazon, all these big companies and small companies have their code on GitHub. So let's say you want to go there and you want to use a code developed by Facebook to do, I don't know, face recognition or something, and you want to at least see that code. You can go there and fork that repository to your GitHub and then bring that locally. You can do that. You can see all the code. It's free, it's open source, it's out there. That's one of the goals of GitHub. The difference here between number 4 and number 3 is that you are not a collaborator on that project. So you do not have the rights, and I mean rights in the sense of GitHub does not allow you to bring this project in your computer, make changes to the code, and push these changes to GitHub and expect that the owner, Facebook, is going to have those changes incorporated there. This is what a fork and clone means, is it belongs to someone else, but you're not a collaborator on that project. You can have a read-only version of it. You cannot really make changes on the GitHub side of it by making changes locally. That is the difference here between 3 and 4. So on 3, it belongs to someone else, but you are invited by the person through GitHub to be a collaborator, which gives you the right to have a copy locally, make changes, and make those changes appear on GitHub as well. Whereas on number 4 here, it belongs to someone else, but you are not a collaborator, so you do not have those rights. You still can have it in your computer and change it, but you cannot have those changes you make be connected to the main one. Also, something interesting is that when you do a fork and clone, you cannot send your changes to them. But let's say the Facebook team has just added a new feature in their code and it's represented on their GitHub, but it happened after you cloned it or you forked it, meaning you don't have those changes yet on your local version. You can always bring in, you can always get pull from that. You cannot get push. So you cannot make your changes available there, but you can always download the changes they made and have the freshest copy locally. If this doesn't make a lot of sense, I hope that it will start making more sense when we actually start working on this. But I just wanted you to see some of the styles of working with Git and GitHub and some of the language behind it as well. So we're going to be doing clones a lot. But if you hear of a fork, that's what it means. It belongs to someone else and you don't have the rights to push to it. That's when we fork it. And just a reminder again, in this class, you will, for the most part, be working alone in GitHub repos that you own, which is the option 2 from the previous slide. And maybe alone is not the best word, because even though we're working alone, you're going to be seeing this more, I guess, and hopefully you're going to also appreciate this, is you're always working with at least your future self. So you're never truly alone. Your future self is also part of that equation. Okay, so if we are, now we talked about git stage, git commit. Yeah, I guess that's it for locally, git stage and git commit. You make changes, you stage and commit. Now, how does that incorporate or merge when we're using GitHub as well? So not just locally, but also remotely. So assuming that you have a clone of that repository on your computer that is connected to GitHub, so your local Git and GitHub are connected, you basically follow the same steps as on the local workflow. So we make changes, git stage, git commit. And then after that, you upload your changes to GitHub by doing git push. That makes it appear on GitHub, whatever you did locally. And if for some reason you're working with someone else that makes changes to the GitHub repo that you want those changes in your local computer, you do a git pull. Sometimes yourself, like you may go on your GitHub page. Sometimes I do this, like I am on GitHub and I think, oh, I should update this README here of this repo. And I make a quick change on GitHub and I commit on GitHub, but then I don't have yet locally that change. So then I need to come to my computer and say git pull that already brings those changes automatically to my Git locally. Okay, so the way that, so let me take one step back here and say, Git works independently of R or RStudio. It is its own thing, right? It has no strict relationship with R and RStudio. So you don't have to use R and RStudio to use Git. In this class, we will be using Git and GitHub through RStudio. There are some helper functions that I think assist in some of the steps of setting it up that in R are going to be a little bit easier, I hope. And the workflow that I want to propose for us to do is called a new project GitHub first. This is a hyperlink. It links to one of the chapters of that Happy Git with R ebook I sent you as a reading material. I want you to be very familiar with this workflow because that's how we're all going to start. Basically, what this workflow here does is, so imagine that, the next exercise that we'll do is going to be on experimental design. So you're going to have at some point in your computer a 03 _ experimental design folder on your class folder for this. So if you remember 01 intro, 02 data wrangling, the next one, I mean, I don't know if that's going to be the exact name, but something like that. It's going to be 03 and then the name of the exercise. I don't want you to create that in your computer first. What I want you to do is go on your GitHub after we have everything connected, which we have not done that step yet. But once that's done, you would go on your GitHub page, create a repository, what you're going to call 03 _ experimental design, for example. Then we will come back to your machine on RStudio, create a new RStudio project like we already did. But one of the options there is to create a project via version control. So you would basically do a git clone when you are creating the RStudio project. And that basically connects that project with GitHub already for you. It saves you some steps there. And then it will work locally like you're doing in this class already. And then you would push your local changes to GitHub. So these are very simplistic steps. If you want a walkthrough of exactly what I mean, you would go on this link and read that page. There's no reason for me to just repeat all that here since you can read as well. But we're going to do this together after we have everything connected, which again, is probably not going to be today. I think it's going to be next class. And every single coding exercise, after we have everything going, connected, running properly, every single coding exercise, we're going to be doing a very similar workflow to what I just described, in that you're going to have a GitHub repo and also a local version of what you're doing in your computer. And you can be, staging, committing, pushing, and pulling if you need to from GitHub. So just a few quick tips here. So this workflow that we're talking about basically involves four Git commands. That is stage, commit, push, and pull. This is a very simple workflow. There are way more functions or way more commands that Git understands and accepts. We are starting with these to go slowly. I could have spent the whole semester teaching you how to use Git in GitHub, and then you would be a pro in that. But then if you don't actually use it, I don't think it's very useful. So I wanted to start simple, using these commands first. And again, Git and GitHub can handle a lot more complex workflows. So you're going to hear, as you're reading about Git and GitHub, you're going to hear about branching. We talked a little bit about forking. There are pull requests. There are many other things that are a little bit more advanced in Git and GitHub. I don't think we're going to get into that a lot in this course. So for right now, we're going to focus on stage, commit, push, and pull. That's a very simple workflow that most people use most of the time. Just some wisdom notes from, I guess, as I've been using Git, I realized some of these and also reading from some other resources is that it is recommended that you commit often. So let's say if you're working on this project, you know, I don't know, like even if you want to say, you know, you worked a couple hours in a project and you got to a milestone that you can close that project and do something else or go home or whatever, that's when, you know, it's a good point for you to commit and say, you know, here on this last couple hours, I did this, I got to this stage, I finished wrangling, I did some ANOVA, I'm checking residuals, I'm training a model, I explore random forest, whatever it is. Commit multiple times a day, and that happens locally, remember, in your computer, and then push less often. So when you push is you're uploading your changes to GitHub. So maybe you can push once a day, right? So maybe you can just push at the end of the day, but do commit in your computer multiple times that day. So you create those timestamps that you can go back to if you have to. This is especially important if you're collaborating, that before pushing, always pull first. What I mean here is before sending your local changes up to GitHub, always get the freshest version that's on GitHub on your computer first. This is especially important if you're collaborating with someone else, and this will save you some merge conflict issues. So what happens is if you and another person are working locally on the same file, exactly on the same row of that file, and you both commit, the first one of you that commit and pushes is going to go through. The second one is going to say, did not work, because you have something different in the same space, same file as this other person has already pushed. So we have to fix that. So to avoid that headache for you, you will get into those issues, I'm sure, as you learn more Git. But to avoid that, always pull first and then push. And I have here, again, some resources. So this is that Happy Git with our resource already have in our schedule for you to get familiar with that. This is a really, really great resource to working with Git and GitHub in R. So I do recommend that you use that a lot. I'm gonna make extensive references to this resource, so please get acquainted with that. This is a link for a Git and GitHub cheat sheet. So it has some of the explanations of what I did, but in a cheat sheet format. And I leave you with this last slide here, which is basically just like some of the most common commands that we're going to be using here. Again, the most commons really are stage, commit, push, and pull. But you know, I also eventually use git status to check the status of my Git. And if I want to read the commit messages that I use for the last commits, I use git log one line as well. This is all on the terminal. We're going to see how to do that both in the terminal and also in RStudio. So this would be the point that we would go to your own laptops and get things installed and connected. I don't think we're going to really have the time to do that in a way that is useful. So I think we can stop today here. I want to tell you the following. So next class, I will not be able to be here in person. I will have to attend another commitment in Tifton. So I'm not going to be here. My plan was, depending where we were in the process here, is that if it was like a lecture like it was today, I would record that, make it available so you could all watch that lecture, even like going through code, and watch on your own. So, you know, so we don't lose a class period. Since we're stopping at a point where actually it's going to be on your side to install things. So if you have a Windows and if you have not installed Git yet, you're going to have to install Git Bash. There are instructions for that in this GitHub Happy Git with R. There's really good instructions. There's also some other instructions and really good material, easy to follow, of how you would create that project first in GitHub, how you bring that over, how you connect your local Git with your GitHub repository. They're all instructions for these. And I think I want to still ask you all to come meet in person. So here in Athens, you all come to this room. And if you have the time and you're interested to try to do these steps that I already sent you on that email on your site, as far as installing things, making sure it's connected and all that, that tutorial is really informative. If I were here, what I was going to do was go through that with you step by step, but I would still be using that tutorial anyways. So I would say if you want to try to do those steps of, and I can send you an email reminding, but if you don't have yet, you need to install Git Bash on Windows. And then you need to do some steps there to connect your local Git with your GitHub page. Those steps are things that we're gonna have to do. So I propose that, so I'm not gonna have a recording for you for the next class period. I propose you all come to class and you all work through that together, especially if you tried at home already and you had issues. Come to class. I know some students here already have some familiarity with getting GitHub. They've already been through some of these steps, so you can help each other. So I think that can be our plan for Tuesday. So still, we're gonna have a meeting in person, you know, where you all can help each other to help to install Git and connect your Git with GitHub. And then the next class, we can start off, you know, if you have questions, issues that cannot be solved here, reach out to me. I will help you to get through that. We'll see what's gonna happen. It's okay if it takes us more than one class period. It is a very important topic on this class that I do want you all to be familiar with and be using Git and GitHub. So even if we have to use more than one class period, that's okay. But let's just dedicate the next class period to make sure you all get things installed and connected and ready to roll. And again, I'll send an email with more information of what links of that tutorial you should be looking at to get this done. All right, so before we wrap up here, let me open a attendance. Oops. All right, I just opened that issue for attendance for today. Make sure you claim your attendance and then you're good to go. I guess any questions or thoughts or issues that anyone would like to speak up at this point? All right, well, I'm gonna
No
close.
questions.
Oh, yeah,
Thank you. Thank you, Dr. Rossi.
thanks, Saker. Appreciate it.
Yeah.
All right, I'm gonna close the online one, but I'll be around for the in-person if anyone has any questions. Thanks, everyone.